I'm glad that I have two screens now. I can see your face. Okay. I really miss my face-to-face class. All right, anyways. Okay, adder, right? So do you see my video there? Oh, why didn't I turn it on? Okay. So, okay, so we talked about adders. So there are two kinds of adders. Half and full. Okay, so half adders can add 2 bits and full adders can add 3 bits. Okay, so when I said 3 bits, I'm saying these 3 bits, 1, 0, 1, for instance. Okay, so when I say 2 bits, I'm saying 0 and 1, something like that. Okay, this is 2-bit addition, this is 3-bit addition. Okay, so if you wanna add, let's say if you wanna add, I'm going to ask you a question here. So if you wanna add 0, 1, 1, 0, 0, 0. So how many half adders do you need?
2.
We need 3 half adders. Okay, so 1 half adder, 2 half adder, 3 half adder. Okay, so half adder can add 2 bits. This is 2 bits, this is 2 bits, this also has 2 bits. So you need 3 half adders here. 1, 2, 3 half adders. Similarly, if you wanna add 1, 0, 0, 0, 1, 0, 1, 0, 0. So how many full adders do you need? You need 3 full adders also. Okay, this is 1 full adder, this is another full adder, this is another full adder. So full adder, as I said here, full adders can add 3 bits, right? So 3 bits, 1, 2, 3. 1 full adders, 3 bits, another full adders, 3 bits, and another 3 adders, or full adders, 3 bits. Okay, so that's what I'm trying to say. Now, so how do you make the full adders from the half adders? To make the full adders from half adder, so suppose this is your half adder here, right? This is your half adder. So why is this half adder? We'll talk about that later, okay? Why is this half adder? Why? We'll talk later, but why is this called full adder? We'll talk now, okay? This guy is full adder. This guy is full adder because it has 2 half adders like this, okay? Even though full adders can add just 3 bits, as opposed to 2 bits in the half adder, we call it full adders because it has 2 half adders, okay? That's the thing. So why do we call it half adders? So this guy, why do we call this half adder? Because, let me explain it here. For the half adder, so what do we do? So if we add 0, we add just 2 bits, right? For the half adder, we add 2 bits. So 0 and 0, 2 bits. The sum will be 0, carry will be 0. And these are the 2 bits we are going to add again. These 2 bits, sum is 1 and carry is 0. And these are the 2 bits again we are going to add. Sum is 1, carry is 0. Again, we are going to add these 2 bits and we get sum 0 and carry 1. Okay, so now the question is, how do you realize sum? So when these two 0, you get 0. These two 0 and 1, you get 1. 1 and 0, you get 1. 1 and 1, you get 0. What kind of system do you need for this thing? For this combination, what kind of gate do you need?
Isn't it like an XOR gate?
Yeah, exactly. So that's why we have here, right? So this is the sum. See, this is XOR. This is the XOR gate. Okay? Yeah, because in the XOR gate, when input is 0, when X input is 0, output is Y. When the X input is 1, then output is Y prime. That's what exactly we have here, right? When this is 0, we have the output exactly same as B. When the input is, one of the input is 1, then the output is exactly the complement of this guy. 0 becomes 1, 1 becomes 0. Okay, that's why this is XOR gate. How about for the carry? For the carry, so what do you do? So look at the carry here. So 0 and 0 gives you 0. So 0 and 1 gives you 0. 0 and 1 and 0 gives you 1. And 1 and 1 gives you 1. What kind of gate is this?
An AND gate.
AND gate, right? So this guy is AND gate. That's why for the sum we use XOR gate. For the carry we use AND gate. That's why what we did. Question here? Okay. Now this is half adder. Now let's go to the full adder now. So full adder, obviously it has two half adders. So this is one half adder. This is another half adder. So let me do one of them. Okay. So I'll just only one here, one set. I'm not going to do everything. Okay. I'm just going to show you this only. So when A is 0, this guy is 0. B is 0, this guy is 0. Obviously, you don't have carry in, right? Because nothing is coming carry. This is the first time we are doing, right? There is nothing carry. So carry is 0 too. You know, when you just add two numbers, right? Let's say 5 and 8. What is the carry from the previous step? Right? So from the previous step, what is the carry here? From the previous step, carry is 0, right? That's what I meant. Okay. So 8 plus 3, 11. Then from this step, we have 1. Carry is 1. But from the previous step here, you don't have no carry. You have nothing, right? So that's why this carry is 0. Okay. So A is 0, B is 0, carry in is 0. So that's what I did here. A is 0, B is 0, carry in is 0. Okay. Now when A is 0, B is 0, what does this guy do? This guy. So this gives you, what will this be?
Does it give you 1?
Really? When this is 0, this is 0.
My bad. 0.
Yeah, so when this is 0, you get exactly as B. Okay? When this is 1, you get exactly the opposite of B. Okay, keep that in mind. So A is 0, your output is, this is your output, right? When A is 0, output is exactly B. B and output match. When A is 1, B and output, they differ by complement. Okay, so let's do that. So when A is 0, when A is 0, B is 0, then this guy is 0 because this is exactly as B. Okay. All right. So then this C is 0. So how about this guy here? C go here and this is 0. Okay. This is 0. Since C is 0, this is 0, right? Makes sense? Then these both are 0. What do you get here?
0.
0. So your S is 0. Your S is 0. Now, how about the carry then? So carry is this guy, right? This is carry. Now let's see. What is the carry? Carry is, this is what? 0?
Mm-hmm.
This is 0. What is this guy? 0? What is this guy?
0.
0. This is AND gate, right? 0 and 0. This is 0. How about this one? This thing, also 0. This is also 0. So you have 0 and 0. AND gate gives you 0, right? So you have 0 and this 0 goes here. And in the case of OR gate, if both of them are 0, what do you get?
0.
0. Okay. So this 0 is this 0 here. Okay. So if you do the same thing again and again, right? So you can fill this table here. So if this is A is 0, okay, if A is 0, B is 0, because now if you add this here, suppose you are adding the second step, right? You have the carry. We talked about the carry 0, now we talk about the carry 1 now, okay? So when you have A and B is both 0, but now you take the carry 1 into account, okay? So that might be the case too, right? So in that case, if carry is 1, what do you get? You have to add 3 numbers now, right? You have to add 3 numbers. What should you get? You should get 0 plus 1. The sum is 1, right? Sum is 1. Then what is the carry? Carry is 0. Makes sense? So when you add these 3, then what do you get? You know what I did here? Let me show what I did here. So this 0, 0 for 0 carry, and this 0, 0 for carry 1. This 0, 1 for carry 0. This 0, 1 for carry 1. See, I'm repeating this. I'm doing 1, 0 for carry 0. Then 1, 0 for carry 1. This 1, 1 for carry 0. This 1, 1 again for next carry, which is 1. I'm doing this again and again. You see the pattern? Okay. So with that, we did the second one, right? So let's do the third one. If we add these 3 numbers, what do you get? You get 0, sorry, sum is 1 and carry is 0. If we add these 3 numbers, you get what? Sum is 0 and carry is 1, because 1 plus 1 is 10, right? 1 plus 1 is 10. So then 1 plus 0, add 3 numbers, sum is 1, carry is 0. 1 plus 0 plus 1, sum is 0, carry is 1. 1 plus 0, sum is 0, carry 1. So 1 plus 1, sum is 1, carry 1. Okay, so we can verify this in this circuit here. If you go through all those things the way we did before, right? Do the different combination of A, B, and C. Okay, A, B, and C. Then you should get S here and C here. Okay, you can verify this. So I hope you can do that. I don't worry about that too much. I really hope that you can do it. So does it make sense so far?
I just have one question.
Please.
In the adder, there's an XNOR gate. And I thought that like the table for an XNOR gate was 1 if it was 0, 0 or 1, 1, and then 0 for 1, 0, 0, 1. I thought it would show 1 when the two outputs are the same, or inputs rather are the same.
Let me try to understand what you said. Okay, this 0, 0. So this is B0, 0. So this is 0, 0. Okay, this is 0, 0. This is 0, 0. Then, so when this, okay. Then your output will be 0, 0. Because this guy just have A and B.
Right.
So then this will be 0, 0. So when this is 0, you get this 0. When this is 0, you get this 0. Okay, so we don't have any role here. Okay, so this C in for this guy here, this guy only. I'm afraid I answered the question.
I think, yeah, that makes sense. Okay.
Did I?
Yeah. You got
Okay.
it. Thank you.
All right. Okay, so now when I say adders, there are two kinds of adders. Okay, so we are talking about full adders now. Okay, so this is full adder. So in this class, we'll talk about two kinds of full adder, kind 1 and kind 2. Okay, I'm not going to give the name. I simply say kind. So one is binary ripple carry. Binary ripple carry adders. Okay, I'll give you the name here in the next slide. Okay, so now the thing is, as you have already realized, if you want to add suppose 4 bits, how many full adders you need, right? So this is just a 4-bit adder. Okay, in general it could be n bit adders, right? So if it is like 1 0 1 0, oops, I don't know, right? 0 0 0. So this is 4-bit adder. Okay, so this is let me call this is, okay, so let me make different color here. Okay, so this is, I will call it A0. This I will call it B0. This I call carry, C in. Okay, so here this is A1, this is B1, this is carry, this is A2, this is B2, this is carry, this is A3, this is B3, this is carry. So did you guys see the logic so far? So I'm going to add these 3 numbers here. These 3 numbers are A0, B0, carry. So A0, B0, and carry. Okay. Then what is the next one here? So A0 is 0, B0 is 0, carry is 0 in this case, right? So then what is the next one here? Help me here. A1, B1C. 0, 0, carry is 1. Carry is 1, right? Then what is the next one here? Help me. 0,
1.
0, 1, and carry is 0. So what is the third one? Fourth one rather. This is 1, this is 0, this is 0. So this is a 4-bit a full adder, okay? This is called, in this picture, this is 4-bit full adder. Okay, this is 4-bit full adder. This partially answer Bridges' question answer also. Yes, he asked one question yesterday in the lab, so about the ripple thing. So 4-bit ripple carry adder, right? So I call this 4-bit full adder, right? Are you convinced with that? Okay, this is there is no doubt this is 4-bit full adder, right? Now the question is, now I'm going to rename this guy and call it 4-bit ripple carry full adder. Okay, it got the adjective here, ripple carry. This is the adjective given to this guy now. Why is that? Because, let me explain that. So, oh, what is this? This is 1, 0, right? Okay, so what do you think this will get here? Okay, when this A is 0, B is 0, what do you get here?
0.
0. So when A is 0, B is 0, what do you get here?
0.
So when this is 0, this is 1, what do you get here?
1.
So when this is 1, this is 0, what do you get here?
1.
1. But this is wrong. You know why this is wrong?
Because we didn't take into account the carry.
Exactly. Now what happens is, so now in the next step, what do you see here? In the next step, this is the first step is wrong. Do you see that? Now second step, what happens is, so when you send A0, let me explain one more time. When you send in A0, B0, you get 0. And you do that at the same time. You send all those A0, B0, A1, B1, A2, B2, A3, B3. You send in exactly at the same time. You understand? You send in exactly at the same time. When you send them exactly in the same time, in the first step, you get this 1, 1, 0, 0, which is obviously wrong, right? You have to wait a little bit time to take the carry into account. So this guy in the next step, what will this guy do? Now, again, in the next step, this will add 0 to it. So when this adds 0 to it, what is the answer?
0.
0. Okay. So when this guy adds 1 to it, what is the answer?
1.
1. When this guy adds 0 to it, what is the answer?
1.
1. And when the guy gets 0, what is the answer?
1.
Now in the second step, we got it right. Eventually you get it right, but you have to wait until it is done. Okay. Suppose there is one more repulse here, right? Then you have to add another one more step here. This is step 1. Then this is step 2. You have to wait another step to get the right answer. Eventually you get the right answer, but you have to wait. Why? Because your carry ripples through, propagate through. That's why we call it ripple adder.
Can you explain or clarify how we got the 1 for the C out between the first full adder and the second full adder? Is that just what we get when we have 2 inputs of 0?
Yeah.
Gotcha. That's what I thought.
So I think I kind of made a mistake here, confused you, I guess. I should have done this, let's say. What I meant by that is this, okay? When Nick asked me question, something clicked in my mind. So 0. So when you add 1 and 1, 0 and 0, 1 and 0, 0 and 0. This is what I meant. Okay. So my thing is exactly like this. This is what my intention is, maybe. I could not show my intention properly. 0, 1, 0, 1, 0, 0, 0, 1. Okay. So 0, 0, 0, 0, you get carry 1. Okay, so 1, 1, 0, 0, you get 1. Then you have carry 0. 1, 0, 1, 0, 1, 1, you have 1. Okay, then 0, this is 0. So this is what I'm trying to show you, but looks like this is impractical, right? Because so you cannot have 0, 0, and 0, then you can suddenly have 1 carry, right? That's impractical. You see that? I made a mistake here. But you guys understand the logic, right? That's what I'm trying to show you. Sorry that I had to choose the practical example, right? Because so when you add 0 and 0, you don't get 0 as sum and carry as 1. You don't get that, right? Okay, that is impractical. Okay, but let's say you got it, right? Let's say you got it. Then this is how you do it. That's what I'm trying to say. Does it make sense now?
Yeah, it makes a bit more sense now.
Okay, thank you. Yeah, this is impractical. You got me. Okay, I have to be more careful next time. All right, so this is done. Now let's go to the now next error is now we did the ripple, right? The previous one is ripple carry. So ripple carry error, ripple carry. In the previous one we did the ripple carry. So what is the problem with ripple carry? Now suppose you have a calculator, right? So you are adding like so many numbers here. I don't know. Oh, that's not what I meant. Suppose you are adding these two numbers. Oh, let me make a binary calculator. Okay, so if you add these two numbers, then your calculator keeps blinking, keeps changing the output, right? I don't know how long you have to wait to get the final answer. That's not good, right? So that's the problem with ripple carry. Eventually you get the final correct answer, but you have to wait for some time. That's the problem with ripple carry error. So that's why, so instead of having that kind of error, what we design here is carry look ahead error. Means so carry look ahead. Okay, what you do here is you send in the numbers here, right? We know these numbers are sent in at the same time. We know that, right? But also at the same time, we have the carry ready to go. We don't care how complicated this system is. We don't worry about this guy. It might be so much complicated, but we don't worry about it. What we worry is, I just need the carry from here right away. Okay. At the time you send in A0, B0, your carry is ready there. At the time your A1 is and B1 is there, your carry is ready there. Because this guy will just calculate the carry only. Okay, just calculate the carry and make it ready. Okay, so everything is ready at the same time. Okay, A0, B0, C0, they're ready at the same time. A1, B1, C1, they're ready at the same time. By the way, we are sending A0, B0, A1, B1, A2, B2, A3, B3, all simultaneously, right? So everything happened at the same time. That's why you don't have to wait for anything. So that's why, so we have this, that kind of error is called carry look ahead error. So you don't have to wait. You just add and get one answer, boom. This is the final. Does it make sense? Okay, now decoder, finally. So yesterday we used one decoder in the lab. That was a BCD decoder. Okay. All right. So what is a decoder? A decoder decodes the binary input. That's what it is. Suppose your binary input is 0, 0. Then you should say, your decoder should say, okay, so both of them are 0, 0. Both of them are 0, 0. That's the decoder says, okay? If the X is 0 and Y is 1, then your decoder says X is 0, Y is 1. If the X is 1, Y is 0, then your decoder says X is 0, X is 1, Y is 0. If the X and Y both are 1, 1, then your decoder says X is 1, Y in 1. But how does it say? Let me tell you how it says, okay? So when X is 0, 0, when X is 0, 0, let me show you here. When X is 0, 0, then this guy goes high, this guy goes low, this guy goes low, this guy goes low. Now what is the language? What is the language this guy talking? When this guy is 1, we have to understand this language now, okay? When this guy is 1, this guy is 0, this guy is 0, this guy is 0, it means, okay, let me translate into English now, okay? That language I have to translate into English now. That English is this. So when D is 0, this 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 guy talk this language in English. Okay. Now when X is 0, so when, okay, now let's talk about the next word here. Oh, so when this is 0, this is 1, this is 0, this is 1. Sorry, this is 0. So what is this language? What is the language this guy talking about? What is the language this guy talks? This means X is 0, Y is 1. This is the language. Okay. So let me summarize here. If this guy is 1, everything else 0, it means both of them are 0. If this guy is 1, everything else is 0, then X is 0, Y is 1. That's the language. If this guy is 1, rest is 0, then X is 1, Y is 0. If this guy is 1, rest is 0, then both of them are 1. This is how this guy talks. We have to understand the language. Meaning, what did it do? In principle, it decodes the binary input. Decodes binary inputs. Okay, how do you design this system then? Let's design that kind of system. Okay. So how do you get when X is 0? When X is 0, okay, let me talk about this, right? When X is 0, Y is 0, the first one is 1, the rest is 0, right? That's what I said. That's what I said. So how do you design this kind of circuit? So when X is 0, Y is 0, what is this guy? This is 1. This is 1, right? Guys, you have to help me here, okay? I'm feeling sleepy. Okay, so this is 1, this is 1. So how about this? This is 1, right? Do you see that? So how about this one? How about this guy here? This is 1. How about this guy here? 0. Do you agree? How about this guy here? This is this one. Guys, help me. What is this one?
E0.
This is 0. How do you know? Okay, this is 0. So how about this one?
That'll be 1.
So how about this guy here?
That'll also be 0.
And how about this guy?
0.
That'll be 0 as well.
Okay. So how about 1 and 1? 1 and 0. 0 and 1. 0 and 0. Because this is an AND gate, right? Okay, these all are AND gate. And. That's why you got 1, 0, 0, 0. Okay, when this is 0, 0, so this is high, everything else low. So when you see the output, this output is high, everything else is low, then you don't have to go to input to understand what the inputs are. You don't have to go to input to understand what the inputs are. Okay. So what is the language that talks? The language it talks is your input are 0, 0. See, you decode the input. Does it make sense?
Yeah.
So you understand the input now. Okay. So you don't have to go to input side to understand what it is. Meaning you have the decoder. With the help of decoder, you understand the input. So depending on how many inputs you have, you can make the different decoder. So you have 2 inputs, then you have how many output in the decoder? 4. It's always 2 to the n. Okay, in this case, where n is, how many n here? 2. 2 to the 2. Suppose you use 3 input here. Suppose you have z here in the same way, right? You have another z here. Then what is your n? N is 3. Then how many help me? How many output do you get here? 8. If you had 3 inputs, then you'd have 8 here. Since we have just 2, that's why we have just 4 output. Does it make sense?
Yes.
Okay. Now I have one more thing to say here before I go to the next slide. So by the way, this guy is, these are the mean term. Remember we talked about mean term, right? In the, what is that called? No. Help me. Carnot map, right? In the Carnot map, we talked about mean term, right? Okay. So this guy is x prime, y prime, this mean term, and this is x prime, y. This is x, xy, x prime, y, and this is not x prime, y. This is xy prime, this is xy, right? Remember we did that in the case of K map. What are these called? What are these called? Mean term, right? So these are called mean term. Now, actually, so when you have 2 input, the output it gives is the mean term. Remember? So when x is 0, y is 0, what is this guy? 1, 1. This is exactly what happened here, remember? That's how we got this 1. So when x is 0, y is 0, what do you get here? Can you help me here? What is x prime? 1, y is 0. This is exactly what happened here, remember? That's why we got 0. So when this is x, y prime, what is this? 0, 1. Remember, you exactly have 0, 1 here. That's why you got 0 here. So when you have 0, 0, you get here, x and y 0, 0. That's why we get 0 here. Actually, you are getting the mean terms. How cool is that? It's not difficult to memorize. Okay, which one is? So that's why, remember, we mean terms, what do you label the mean terms? What is the letter you use? M0, M1, M2, M3? That's what we exactly had. M is replaced by D. This is D0 is M0, and this D1 is M1, D2 is M2, D3 is M3. That's what it is. Guys, question here, please.
Makes sense.
Okay, good. Okay, now let's use the decoder for, so one of the use, there are several uses of decoder. Let's talk about the use now. What are the uses of decoders? Number one, implement the functions. So we already know, so output of a decoder is mean term, right? Let me write here. Output, this is what we concluded last in the previous slide. Output of a decoder are mean terms. So that makes me feel so good, because when you have mean terms, right? Remember what is the SOP? Any function can be written in terms of mean terms, right? That's the SOP. So I'm excited now. Since output of a decoder are mean terms, that's why I can implement decoder. I can use decoder rather to implement any function. Does it make sense? Okay. So suppose you wanna implement this function now, for instance. So how many? What is the decoder you need? What kind of decoder do you need? How many input? So depending on how many variables here, you have X, Y, Z, right? That's why you need 3 input decoder. So by the way, you don't call it 3 input decoder. You always say 3 and 2 to the 3. So 3 times 2 to the 3 encoder. This is the name given to the encoder. Sorry, not encoder, decoder. Okay, this is the name given to the decoder. So input and output times in between. Input times output decoder. This is how you design how you give the name to a decoder. Okay, so it has 3 input, it has 8 output. That's why we call it 3/8 decoder. Okay, we need 3/8 decoder here. Okay, so now this circuit is exactly this circuit, but with one extra output. One extra output, right? One extra output. Of course, we have more extra input. Sorry, what's wrong with me? One extra input and more output. Okay, when you add one extra input, you have to add 4 more output, because you have to have in total of 8. Okay, that's what I did here. So we have 3 inputs and 8 outputs. So what do those output represent? Again, mean terms. Okay, remember, if we have help me here, what is that called again? K-map, right? In the K-map, what was there? M0, remember? M1, M2, right? Those kind of thing. So here, this is M0. Sometimes F0, sometimes D0, sometimes M0. See, it has different names now. Okay, F0, D0, M0. So in this case, we should have said D0 rather, right? So this is D0. D0 is X prime, Y prime, Z prime. So what is your D1? D1 is X prime, Y prime, Z. What is your D2? X prime, Y, Z prime. Then D3, X prime, Y, Z, and so on and so forth. Now, can you use this guy to make to implement this function now? How do you implement? Now you have the output ready, right? You have the output ready. Now you have all these guys ready. This is ready, that is ready, this is ready, this is ready. Then what do you need to do? Just you have to do just one more thing. You have to do just one more thing. What is that one more thing? Add them all together. Add them. Look, plus, plus, plus. You have to add them together. How do you add them together? That's all. If you have one OR gate with decoder, you can implement any function. How cool is that? You can use decoder to implement any function just by adding one OR gate. Isn't that cool? I loved it. Okay. All right, so now let's talk about the decoder as permanent memories. So I know you guys have heard about memory, right? So RAM, I don't know. What is the random access memory? I think that's it, right? Random. You have heard lots of kinds of memory, right? So I'm not going to go over there. So here I'm going to talk about read-only memory. So it's not RAM, it's a ROM actually, okay? ROM. Read-only memory. ROM. But what kind of ROM? It's programmable, okay? We can program it. So we call it PROM, okay? So we can program it. Now this is what this decoder looks like. This memory looks like. Okay, we use the decoder. This is the second use of decoder. Number one, we can use decoder to implement a function. Number two, we can use the decoder to make the permanent memory. Okay. Okay. So if you wanna, so let me show you how it looks. First of all, so you'll have similar homework also, guys. Okay, please pay attention to it, everybody. So here we have the decoder, right? So you know what it looks like. Okay, you already know this, right? So this you have. Remember, we have X and Y. This is X. This is Y. Okay. Ah, so cute. Okay.
She's a bit needy.
Okay. So XY, these are the inputs, and what is the output here? D0, D1, D2, D3. These are the output, right? So this is what this looks like. Okay, this is this guy. Okay, I'm lazy now, so I'm not going to do this again and again. Okay, so instead of this, I'll keep doing this now. Okay, so I'm not going to draw that. That's very tough to me. You know, I'm lazy, so I just make circles and squares and those stuff. So this is X, this is Y. And this is D0, you know, this D0 is X prime, Y prime. So this is X, Y prime. Oops, X prime, Y. This is X, Y prime, and this is X, Y, okay? So now So I don't have to explain anything about this guy, right? So anything about this guy up to here is done, right? This part is done. Okay. Now what I did here is, now I extend the output here. See, I have 4 outputs extended. This is number 1, this is number 2. See this line? This line I'm talking about, this line. Okay, number 1 line. Oops. Number 1 line, this is the wire. Number 2, number 3, number 4. I have 4 lines here, okay? Then I'm connecting each of them to the OR gate. Remember, this is OR gate, right? This is your OR gate, this is your OR gate, this is your OR gate, this is your OR gate. See, this OR gate, how many inputs does this OR gate have? 4. And these are all connected to these outputs, okay? This is connected to D3, this is connected to D2, this is connected to D1, this is connected to D0, okay? So this is connected to, in the same way, you see all the connection here?
Why is there a gap between some of them?
Okay, forget about the gap, please, for now, okay? I'll answer this question in 30 seconds. Okay? So these are all connected now. Okay? Now, this is the brand new. This is a brand new memory you got from the store. I don't know. Best Buy. I don't know. You got this memory from Best Buy. Okay. Now, what you need to do is you want to program it, right? You want to program this memory. This is empty. Right now, this is empty. So in order to program it, now as you noticed earlier, I programmed this memory here. To program this memory, I blew the fuse here. Boom. 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 I blew the fuse here. Okay. So why did I blew the way I blew? I'll talk about that in like 15 seconds. Okay. Now, so because I did that because I wanted to get this output. I wanted to store this data in my memory card. Remember, computer doesn't understand anything other than 0 and 1. Everything is 0 and 1, right? We have to decode eventually, right? So I want to decode 4 words of 4 digits. This is one word of 4 digits. This is another word of 4 digits. This is another word of 4 digits. This is the 4th word of 4 digits. I want to store 4 words of 4 digits. Okay. So what kind of words? What kind of words they are? The words are, the number 1 word is 1101. The second word I want to store there is 1001. The third word I want to decode store is 0010. And the 4th one I want to store is 1111. If you wanna store these 4 words, then you have to blow the fuse the way I blow. Meaning, if you wanna store these 4 words, then you have to blow this fuse, you have to blow these 2 fuse, you have to blow these 2 fuse, and you have to blow this fuse. If you blow exactly the way I showed, then that acts as memory, which can store exactly these 4 words. But the question is how, right? Let's see how. Okay, I'm going from example, first example, then because most of the time in electronics, if you start from example, it will be easy to understand, okay? So that's why I'm going with examples here. So let's see. So how come if you wanna store this, right? If you wanna store this, why do I have to fuse? Okay, why do you have to fuse this guy here? So when A is 0 be okay. So when A is 0, A0 is 0, A1 is 0, right? So let's talk about this one first, right? Okay, let's talk one at a time. It means A0 is 0, A1 is 0. Then what is your D0? Help me here. What is your D0? Now you gotta help me here, please.
0.
The D0 will be 1.
1 and rest will be 0, right? This is just a decoder. Okay. Now when this is 1, this guy is 1, right? This guy is 0. This guy is 0. Then what do you get? 1, 0, 0. Or
One.
get
You
1.
get 1.
1, right? Okay, now this guy is what? What is this guy?
1.
1. What is this guy?
0.
1 and 0.
1.
Or get
1.
1. So this guy is what?
0.
0. This guy is
0.
or get.
0.
So this guy is
1.
this is 0. This is 0. Did you get this one? 1, 1, 0, 1.
Mhm.
Now, okay, let's change it to 0, 1 here. 0, 1. This is 0. This is 1. Now help me with the decoder. With the decoder. What is this guy? Oops. This is 1. This is 0. This is 0, right? Now, what happens here?
The output of O3 would be 1.
Okay, so this this is 0. This is
1.
1. This is 0. This guy is
1.
so this guy is
0.
this guy is
0. 0.
0, 0. This guy is
0.
0, 1, 0. This guy is 1, 0, 0, 1.
So how does the memory form those gaps?
Okay,
for the
I'll
output?
answer this question in 1 minute.
Sure.
Okay, let me finish this first. Because if I answer this question, you won't listen to me anymore. It's that exciting, okay? All right. So if A1 is 1, this is 0, then what do you get here? 0, 0, 1, 0. Right? So let's see. This guy is 1, right? This guy is 1, but this is not connected. Everything else is 0. 0, 0, 0. What do you get here? 0. Make sense? So how about here? This is 0. Then this is 0. This guy is 0. So how about here? This is 1. This is 0. How about here? 1. How about here? This is 0. This is 0. This is 0. See? 0, 0, 1, 0. When 1, 0, then you get 0, 0, 1, 0. Does it make sense so far? So I'll answer the question in 30 seconds now. So I'm almost done. Then finally, what is there? 1, 1, right? So 1 is 1, 1. This is 0. This is 0. This is 0. This is 1. So then because of this one, this is 1. See, this is connected here. Since this is connected here, this is 1. Since this is connected here, this is 1. Since this is connected here, this is 1. You get 1, 1, 1, 1. This is very easy. Now, Austin, I'm going to answer a question. Yes, my today's goal is make you happy. Okay. Now the thing is, how do you know which one to blow, right? That's your question. So look at this. 1, 1, 0, 1. 1, 1, blow. 1. 1, 0, 0, 1. 1, blow, blow, 1. 0, 0, 1, 1. Blow, blow, 1, 1. 1, 1, 0, 1. 1, 1, blow, 1. If you choose this way, so depending on what you want to store, right? Depending on what you want to store in that memory, you blow the fuse accordingly. So if you want to store particular these 4 words, then you have to blow accordingly like this. But in the homework, I'll give you something different, some different words, and you have to blow accordingly. Question? I'm ready to answer your question now.
So those OR gates, they're created and they come originally with those leads missing, like those gaps.
No, they don't.
Or do you program that?
Yes, that's what we do. So that's a very good question. So these are called programmable connections. So the 4 decoders outputs are connected through programmable connections. Okay, when programming the Prom by the user, a different circuit not shown here blows the fuse.
So once you program it, you can't change it.
No, that's why this is called
Read only.
Does it make sense?
Yep.
All right. So there are many kinds of ROM. Okay, some of them uses erasable floating gate technology. Okay, so it means you can erase the data we had and you can reprogram it. Okay, so that kind of read-only memory are called EPROM. Erasable, programmable, read-only memory, EPROM. So how do you erase it? So removing the gold sticker and signing UV light erases the memory. See, there is a gold sticker here. Remove it and shine the UV light. Okay, this is old technique, right? But nowadays we use electrically erasable. Okay, we can erase electrically. And that kind of ROM is referred to as electrically erasable PROM, or EEPROM, or in short, E squared PROM. Remember the flash memory we use nowadays? This is also a modified E squared PROM. Okay, there are several memory, as you can see, right? We talked about this memory. So programmable PROM, we talked about it. You know, there are E squared PROM, there are flash memories, and you have heard of random access memory, right? Random, non-random, all kinds of stuff. There are a lot of stuff here. Okay. So the main characteristic of E squared PROM is we can erase the large regions at once. That's the advantage of our, you know, flash memory. Remember, we use flash memory nowadays. Okay. Okay, so now next one is, oh, we done? Really? All right, guys, so I'll stop this on time today.